Yeah, this is going to be the final week of number 3. We are going to wrap up number 3. Diophantine equations are in front of us, guys, where we are mainly interested in finding integer solutions. So where does the name Diophantine come from? It comes from the Greek personality who was... Okay, let's dive into the linear Diophantine equations. Hello everyone, welcome to the third week of our learning towards IOQM. Yeah, this is going to be the final week of number 3. We are going to wrap up number 3. We have covered almost everything from the basics, and in future we will definitely come back to number 3. We'll do maybe intermediate or advanced problems, so we'll do a lot of things. Number 3 isn't gone, but this week we are going to wrap up the theory session, and this week is going to be very interesting. Diophantine equations are in front of us, guys. So this is one of the most fascinating stuff in number theory. Yeah, different kinds of equations. Papers have been written. Many Diophantine equations are still very hard to crack, right? So in today and in the next couple of days' videos, we're going to dive into a few types of them, Diophantine equations. So first of all, what is that? To learn about it, Diophantine equations are two or more variable equations where we are mainly interested in finding integer solutions, right? Integer solutions. We are mainly interested in finding integer solutions. So that is Diophantine equation. So today we are going to do linear Diophantine equations where of course the equation is a linear one. And in the next couple of days, we are going to explore briefly, at least, how to deal with other kinds of Diophantine equations. And it's going to be very, very interesting. So stay tuned and let's move on. So where does the name Diophantine come from? It comes from the Greek personality who was, alive 2000 years ago, around 1800 years ago at least, right? He was a Greek mathematician. Diophantus, I don't know how to pronounce that. It's a Greek name, and he was one of the first who developed arithmetic. We don't know much about him. That is unfortunate. Not much was documented about him. Maybe he was not that famous compared to other mathematicians at that time, like Eratosthenes. Many stories are available around Eratosthenes, like how he found out Earth's circumference and everything. So it's a very fascinating stuff. So this guy is relatively not so famous, but at least we remembered him as mathematicians with this Diophantine equations. So how is he one of the first who developed arithmetic? So he is the one, his teacher probably, there's a story. So there are only a few anecdotes which are revolving around him. So one of them says that he solved a very complicated question given by, it's not complicated, if my father is this much age, this many years ago, that kind of a question. So he solved it very easily because at that time, taking a variable to be x, right, an unknown quantity can be taken as a letter or something, is a new concept 2000 years ago. Come on, so it was not developed. So he was one of the first who took a dummy variable. You understand, dummy variable? So we don't know what the quantity is, so let us say it is x, and then let us do the required calculation. Now it is very easy for us to recognize that, because since the class 7 or 8 we are learning algebra stuff, we are learning about ABC being used in mathematics, which were generally dealing with 1, 2, 3. So he was one of the first who actually used that. So he developed arithmetic from that. Like, you see, you must understand that maybe he didn't have a major support in that. Yeah, but he still developed it. It takes a lot of courage to do something which is not being done around you, isn't it? So that's his credibility, which I would say. Okay, let's dive into the linear Diophantine equations. So we want to find the integer solutions. As I said before, Diophantine equations, in Diophantine equations, we are mainly interested in doing integer solutions. And linear Diophantine equation is simply ax plus by equal to c. As simple as that, nothing. So first of all, we want to think about when a solution will exist. Here the variables are x and y, of course, for x and y, right? That shouldn't be a doubt. So look at these. I hope this is visible, right? Let's look at the first one. So the first one says 2x plus 10y is equal to 17. Now, when does the solution exist? If you want to check, does the solution exist for that? Can x and y be integers and this be holding? So in the left hand side, if you see, I can take 2 common. So it will be x plus 5y equal to 70. Now is this possible? This is not possible, right? Because this is an integer. So 2 into an integer is an odd number is not possible. So that's common sense, and we say that no integers exist. No integers exist. So we say this is an unsolvable Diophantine equation. It is not solvable. Because in Diophantine, the moment we use the term Diophantine equation, if this equation is a Diophantine one, we are looking for integer solutions by default, right? I want to make that absolutely clear. This is by default, right? The moment you see this term Diophantine, that is by default we are dealing with only integer solutions. Okay, let's look at the second one. It says 3x plus 12y is equal to 60. So I can take 3 common. So x plus 4y is equal to 60. So I can cancel out 3 and this will be 20. So x plus 4y is equal to 20, and we do know that an integer solution exists. What is the integer solution? Immediate one. If you take x0, then y will be 5. 0 comma 5 is a solution. So we definitely have integer solutions, and we can get more solutions. You can think of more solutions, right? So pause the video and tell me in the comments what is the solution which clicks to you next. Yeah, think about it. Okay, now that's an interesting one. Now how do we actually solve these kind of things? That's what we will deduce. How do I get more solutions of this? Okay, first let us look at this one. So is that solvable? So we first have 1 comma 1 as a solution, isn't it? Think about it. Immediately you must be saying that 1 comma 1 is a solution. Okay, in the previous one also we have 0 comma 5 as a solution. From that, can we extend it to more solutions? So let me get to this one particularly. Since we have x plus 4y is equal to 20, I can write x as 20 minus 4y, which is 4 into 5 minus y. So if I take any integer y is equal to k, then x is equal to 4 into 5 minus k is always a solution. We have a general solution. So whenever this is possible, and especially in linear Diophantine equations, it is always possible to get a general solution. You can always get a general solution. So this was pretty easy, right? Whatever value you put k belongs to integers. Whatever value you take for k, a corresponding value of x can be produced. It is always possible, and both are integers, x and y, if you look at it. So let's try to do that for this one. This is not so easy looking. Okay, so let's see what happens. So I can write 5 as 2 plus 3. That's the thing. That's why 1 plus 1 is working. Now I can write 2x plus 3y is equal to 2 plus 3, right? And that should imply 2 times x minus 1 plus 3 times y minus 1 is equal to 0. So this equation I'm writing it like this. Yeah, makes sense. Now you must carefully note what I'll do next. So this means 2 times x minus 1 is equal to minus 3 times y minus 1. In other words, I am saying x minus 1 by 3 is equal to y minus 1 by minus 2. Can I say? I'm just cross multiplying 3 and 2 here and there. Now I can take this as an integer, yeah, belonging to the integer set. Do you see what is happening? Immediately, do you see what is happening? Immediately, you can write x minus 1 by 3 is equal to k separately, and y minus 1 by minus 2 is equal to k separately. So, okay. So, what do? I take x minus 1 is equal to 3k, y minus 1 is equal to minus 2k. So x is equal to 1 plus 3k, y is equal to 1 minus 2k, and both are integers. Both are x comma y belong to, right? Is that understood? That is simple. So in a very similar manner, we will try to find other solutions, like for every, this thing, what do we say, for every linear Diophantine equation, we can always get a general solution like this. Okay. Now look at that. Okay. We have 4x minus 6y is equal to 14. So I can definitely take 2 common and cancel out 2. So that should imply that 2, if I take common, this is 2x minus 3y is equal to 2 into 7. That will imply that 2x minus 3y is equal to 7. Now can you find one particular solution? Can we find one solution? I can definitely think of probably x is equal to 2 and y is equal to 1. This will work, isn't it? So y is equal to minus 1. Yeah, okay. So y has to be minus 1. So I am doing 4 plus 3, isn't it? Y is equal to minus 1. So I will be doing 4 plus 3. So I can write it as, now I will write it as, we use another color, 2x minus 3y is equal to 4 minus 3. So I can write it as 2 times x minus 2, I will just bring it this side, minus 3 times y plus 3, I suppose. Yeah, works. Plus 1, sorry, plus 1, plus 1, right, is equal to 0. Now I'll do exactly what we did there. So I have x minus 2, 2 times x minus 2 is equal to 3 times y plus 1. That gives me x minus 2 by 3 is equal to y plus 1 by 3. So that immediately tells me that I can take this to be some k belonging to the integers, yeah, and then I get x is equal to 2 plus 3k, y is equal to minus 1 plus 3k. Whoa, I think I made a mistake. This is supposed to be 2. What is this? 2k. So this is the general solution, right? This is the generalized solution. So it does seem that whenever we are able to get a solution, whenever the solution will exist, if we have one solution, we can always find a generalized solution. So do you notice something? This is totally dependent on the initial solution. 2 minus 1 is there, and then the general part comes out. This should be observed here as well. This is 1 was a solution, and hence we extended it to a generalized version. Did you notice that? I hope you did, right? Now let us try to generalize this for any a, b, c. Yeah, let us generalize for any a, b and c. So how do we do that? Now first of all, the condition is that if D is equal to GCD of A comma B, then D must divide C, right? Why? Like, it's not a random mathematical statement. Let's try to look at it carefully. So if this is an integer, then if A and B have a common divisor, if D divides A and D divides B, this is one of the properties which we did in GCD class, then D must divide AX plus B. Why? So that does imply that D must divide C, right? That is a condition. If this does not happen, then there will be no solutions, because here we are taking x and y to be integers, right? Is that understood? Okay, now let's try to solve what happens when this is happening, right? Let's say we cancel out the D. So I'll write everything in terms of D. A by D, X, B by D, Y is equal to C by D. So let's say A by D is some A dash, B by D is some B dash, C by D is some C dash. Right, this has to be an integer. So that will imply that A dash X plus B dash Y is equal to C dash. This is exactly what we did in this question. We took out 2 common. 2 was the common divisor of, greatest common divisor of 4 and 6, minus 6, same, right? So we cancelled out that. So we see that 2 and minus 3 are of GCD 1. So that's what I'll do here. I'll note that A dash comma B dash ka GCD is 1. Yeah, so the GCD is 1. So we know one fact, that if GCD of A dash comma B dash is 1, that implies that there will exist x naught y naught, or x dash y dash, let's say. What am I doing? X dash, let's say, such that A dash x dash plus B dash y dash is equal to 1. This happens, no? We saw that, didn't we? this is something which we have already seen, and of course these are integers. So I'll multiply C dash, implies in the box, right? So that implies A dash C dash X dash plus B dash C dash Y dash will be C dash. Now I will take C dash X dash as X naught and C dash Y dash as Y naught. So A dash X naught plus B dash Y naught is equal to C dash. So what we get from this is that there will be a solution for A dash X plus B dash Y is equal to C dash whenever if A dash comma B dash GCD is 1, right? There will be a solution all the time, This is what we have reduced to. Let us recap what we did. So we first have this equation. Now you will be able to follow, you will be able to relate this everything with the previous one. Now if you see in any question, here the 1 comma 1 must exist because that's how it is, right? Okay. Anyways, and if you see for this there will exist no equation. If you look at 2x plus 10y is equal to 17, there will be no equation because 2 and 10 don't have even if you take out 2, so it will be 1 and 5, right? 1 comma 5. So for this you may find 1x dash plus 5y dash is equal to 1 is definitely possible. It is possible. But to get that to be 17 by 2, if I want 17 by 2, then I must multiply 17 by 2 x dash plus 5 into 17 by 2 y dash. Now this need not be integer. Equal to 17 by 2 will be there, but this won't be integer, not integer. Do you understand that? Do you understand that? Okay. All right. Okay. So we have till here. Now this gives us the initial solution. We got the initial solution for each of that, right? Now this x naught comma y naught is the initial solution. We will call this x naught. We call this x naught and y naught the initial solution. Now this initial solution thing will also happen in one of the other Diophantine equations called Pell's equation. So we will deal with those things in the next video, and that's also a very fascinating concept. Pell's equation is a quadratic in x and y. Okay. So what do we do with this? So now I can write this c dash as that, and if I multiply, I multiply D, the GCD of A and B, then we simply get AX naught plus BY naught is equal to C. So what do we have so far? We have so far what we got is for AX plus BY equal to C. This was given. We have D equal to GCD of A comma B divides C. Hence there will exist x naught comma y naught such that ax naught plus by naught is equal to c. Now from that we want to find generalized solution. Yeah, okay. So now put that here. So ax plus by, I'll maybe change the color. Let's use light red. Okay, so we have ax plus by is equal to ax naught plus by naught. That will imply that a times x minus x naught is equal to minus b times y minus y naught. Yeah, as we did before. That will imply x minus x naught by b is equal to y minus y naught by a. That can be taken as some k belongs to integers. So that will imply x will be x naught plus bk and y will be y naught plus or minus, right, it should be minus minus ak. This is the general solution. I hope you are noting that I am naming these something. This is called initial solution. Yeah, x naught and y naught are initial solution, and from that we get this. Yeah, is that clear? Now you will notice that this will satisfy the equation. This will satisfy the Diophantine equations. Right, I hope this is clear. I'll give another an assignment for this. I will upload other assignments for the other videos as well. I hope you are able to follow this through. If not, then please contact me at this Aniruddha Chakri in Telegram. Yeah, and in the next video we'll deal with more interesting Diophantine equations. We'll deal with a by x plus b by y is equal to c, this kind of thing, or maybe x square minus dy square is equal to 1 kind of thing. Does this have integer solutions? That's the interesting thing, right? So we won't extensively do this, because this I did in my bachelor's, this I did in my B Math, and I also extended the study on this in M Math. So these are a little bit high level stuff, right? So the existence of a solution is tough to say for this one, but definitely we can always say talk about if there exists a solution, then how to generalize a solution, right? If we have a solution x naught comma y naught, the moment we find a solution, how do we generalize the solution? That we will talk about in the next video. We'll also do a couple more things. We'll deal with Pythagorean triplet, x square plus y square is equal to z square. Generalized solution for this is also a little bit tough, right? But we will do one variant of that, and I'll help you do with all of that. We have 3, 4, 5, we have 5, 12, 13, right? So can this be generalized further, will be the attempt. And then we have another one, exponential stuff, right? We have a power x plus b power y is equal to c. So how do we solve that? That's also a very interesting thing to do. So I hope you enjoyed this video. I'll meet you in the next video. Right? Bye bye. Have a good day.